All right. So Destiny was just asking about the exam. And I was telling her what we're going to hopefully be doing. I'm going to troubleshoot it a little bit more this afternoon with Ming. Um, it looks like yesterday I was able to find an option in the quizzes where it allows your answer to be an uploaded file. And so if this works, this exam will look like a quiz whose only question is the PDF of the exam, and your answer is going to be an uploaded file. That way we can do the time thing, we can do the window thing, I can do the time extended for people who get that, and I don't have 80 some odd emails and trying to sift and sort. It'll just be automatically tied to your name in Canvas. So that's what I'm hoping to have in place for Monday. Same window, 8 to 12. You know, you still get the extra time to do it for the uploading and everything. But this way, you won't have to worry about emailing me. You'll just upload it straight into Canvas. Now, since Destiny, you asked that question, does that make sense to you?
Yeah.
Does anyone else have a question about what that might look like? Like, I guess right now, before I tell you what it looks like. That's kind of a weird question.
So does that mean we're gonna have to upload and take a picture of every question?
No. It'd be every page, just no, because it's gonna be one question. The one question is, get this PDF, take the test, right?
Uh-huh.
And so it should be just like the last exam, except instead of emailing me the PDF, you'll upload that PDF into Canvas.
Okay.
And this will be nice, I hope nice, because I also sent out an announcement, I think you guys got it, about this cam scanner.
Yes.
And was it you, Destiny, or was it, wait, or was it?
Me,
It was you,
Yadira.
Yadira, that's right. Yeah, so Yadira really turned me on to this cam scanner. And she basically convinced me to use it. I went ahead and looked at it online, and it turns out they're giving it away to students with a valid EDU account. So you just use your school account, and it'll go like, oh, you're a student, great, here it is for free. And it apparently automatically resizes any picture you take to a reasonable size limit. And I think you took 6 pictures, and it was like a couple of megs or something like that. It was really nominal. And so it made downloading a whole lot better for me, given my limited internet speed. And also, for those who had much larger files that sent the last exam to me, when I tried to send you a PDF of your exam to show you what you missed, some of yours were too large for me to actually send out of my server. My server goes, nope, that's too big, you can't do it. How you were able to send it to me in the first place, I don't know, but I could not upload and send back out. And so for those people, if you wanted to walk through it, we can do it in maybe the office hour or something like that, or a quick little private one if you don't want anyone else to see your mistakes. So I highly encourage you guys to look at Cam Scanner. It looks like it works with any operating system on a phone. And since it appears everyone had a phone to do it in the first place, this might be something you want to do. If you have questions, Yadira Rivera, she's your girl. And so if, let's see, Canlis says you can scan your notes in an app. Kim says thank you with prairie hands. Anyway, so Yadira, at the end of this, if there's anybody who wants to pick your brain, maybe after we're done recording, or maybe while we're still recording at the end, you can answer their questions or something.
Okay.
Because you're awesome like that.
Good morning, everybody.
Oh, Jordan's here. We can start.
Thank you.
So, yeah, I have to say I'm really liking this crew. We're making this transition our bitch. we're doing this. All right, let's see. So again, the exam will be Monday. The stuff I'm going to go over today is not going to be on the exam. However, you might still find it somewhat helpful because it's going to reinforce this whole Avogadro number turning those mystical, magical AMUs into grams per mole and what it means to be a mole. I should probably have already done this ahead of time, but I was too busy troubleshooting stuff around home, so I'm gonna have to make a page here. Let's go to Chem 110. Let's make a new page. And we're gonna call this mass to mole to mole to mass. Ta-da. And I'll worry about the date in a minute because I didn't realize I wasn't doing that. All right. Move everything over here. Before I get started, do we have any other questions that I have not fixed? And is everyone seeing my screen since I'm doing too many things at once?
Yes.
Yes.
Cool. Cool. All right. Glasses on. Let's do this. Okay. So what I'm going to do right now is lay down some groundwork for us, specifically around this whole why did we do what we did with Avogadro's number, with balancing equations. You know, what is it all coming down to? And I said many weeks ago that one of the things that we're going to be able to do is not just say what we're going to bake, but we're going to say how much we're going to make. And so I want to start out with something called the mole to mole relationships. So we have mole to mole relationships. Now I'm going to start out with something that we all know and love. 2 hydrogens plus an oxygen. What type of reaction is this? For those of you who didn't say anything, combination is the correct answer. And on the other side, hopefully you know that you combine those 2 things to get good old-fashioned water. Now, show of hands, just kidding. Show of hands, how many people in their brains have been thinking this whole time that that's 2 molecules of hydrogen plus a molecule of oxygen making a couple of molecules of water? In any normal situation, I would say, hey, somebody's doing it. Yeah, Kim's raising her hand. You know, here's the deal. This is how we've been trained up to this point. We should be thinking of this in terms of just one little hydrogen over here with this little H and H and the oxygen with this double bonded thing, making a good old fashioned water molecule, right? Well, I don't know why I put an OH. You do this something like this. This is what we've been thinking about. You get a couple of those, you're gonna make 2 of those. You know, that's all fine and well, except for thinking of things on a molecular basis is really tiny and really hard. So what we're gonna do is we're gonna use Avogadro's number to sort of scale everything up to what we can see. So we used to think of this in terms of 2 molecules H2 and 1 molecule makes 2 molecules of H2O. That is probably what jumped into all of our heads, and not surprising because, I mean, technically I've been training you guys to think that way. But what I want us to do now is I want us to now say, we don't want to look at it atomically, we want to look at it as something that we can actually measure. And so what we're going to do now is we're going to use Avogadro's number to scale them all to reasonable size. And so what this really means for us is now those coefficients are now moles. And I always like this crazy irony. Molecules become moles. And so instead of thinking about this in just terms of molecules, we're going to now look at this and say, instead of 2 molecules of hydrogen plus a molecule of oxygen makes 2 molecules of water, we're going to now say that's 2 moles of hydrogen plus a mole of oxygen makes 2 moles of water. Now, the reason why we do that is, again, we don't want to think about this atomically, we want to think about it holistically. This is one of those SLOs, from the micro to the macroscopic. Now we're going to make it big. We spent all this time looking at it at the small, let's go big. We also spent some time balancing the equation. And here's the thing, when we have a balanced equation, we now have a ratio. I know you guys love those things from the math days, but essentially what you can see here is you have a 2-to-1 ratio of oxygens, or you have a 2-to-1 ratio of waters to oxygens, or you have a 2-to-2 ratio of hydrogen to water. And when we have these ratios, we can now start setting up what are called molar ratios. So keeping that equation in mind, let's look at what the molar ratios look like. So the molar ratios from the equation above. If we look at the molar ratios from the equation above that disappeared because I had to scroll, we can look up there and we can say that we have 2 moles of hydrogen per every 1 mole of oxygen in that equation. And you might remember that per means divided. Now, you could also think about this another way. You could look at it the other way, that there's 1 mole of oxygen per every 2 moles of hydrogen. You can think about it either way. And it doesn't matter if you're starting on the left and going to the right, or starting on the right and going to the left, or staying with everybody on the left like we're currently doing here. As long as you talk about one in terms of the other, that's making a molar ratio. So there are 4 more ratios that we can write out, and this would be the last time we actually physically write them all out. So we can have 2 moles of hydrogen per every 2 moles of water, or 2 moles of water per every 2 moles of hydrogen. So we've now compared hydrogen to oxygen and hydrogen to water. Let's finally compare oxygen to the water. We know that you can have 1 mole of oxygen per every 2 moles of water, or vice versa, 2 moles of water for every 1 mole of oxygen. And here we have now 6 molar ratios, all relating one species to another one, depending upon your point of view. The reason why we do this is by having a balanced equation, right up here, by knowing the certain amount of moles of one object, you now know the moles or the amount of every other object in that balanced equation. That's the reason why we did this. Input equals output. Conservation of mass. What goes in must come out. All of whatever's in the reactants must be on the products. These ratios are maintained and they are absolute. So that means if I tell you you have 2 moles of hydrogen reacting, you know that you'll have 1 mole of oxygen reacting. You know you'll make 2 moles of water. No? Am I glitchy?
No, not for me or
I
not.
hear you.
So I see some people I see some people saying whether or not I had glitchy sound or not.
You're not glitching to me, so I don't know if it's theirs or.
It's
Yeah,
only every
usually-
once in a while.
I usually default to mine being bad. It's looking like it's good right now. If I start getting glitchy again, you know, throw it up in chat just in case, and I'll double check my internet speed. Right now, we're actually humming along. But I do get very sensitive to that because country folk out here, you city folk have your broadband and your fancy highfalutin. I got mice and hamster wheels. All right, let's take a look at an example of how we might use this molar ratio situation. I'm going to say if 7 moles of hydrogen react with oxygen, how many moles of oxygen are needed how many moles H2O are made? Now, I always pick this one because some of it looks very intuitive, and it should be intuitive. You could look right back up at that reaction where we have the 2 hydrogens plus the 1 oxygen making 2 waters. And we should be able to just deduce this with our brains. So if I have 7 hydrogens, how many waters do you think I'm going to make?
7.
7, right? If that ratio is the 2 to 2, then 7 to 7 naturally follows. So hopefully you guys are already going like, wait, is this a trick question? No, it's really that easy, okay? Of course, the first one is always easy. The first one's always for free, right? So let's go ahead and do this. The first question was how many moles of oxygen are needed? Let's do it mathematically. So we know we're going to look for moles of oxygen. And we look up there and say, is there anything up there that looks like moles? Of course, the 7 moles of hydrogen. So I'll start with that 7 moles of hydrogen. And now, no numbers. I just want units. Remember, this is units conversion straight from the first exam. What units should I put on the bottom of this conversion?
So hydrogen, mole of hydrogen.
Yeah, moles of hydrogen. And of course, then we'll want moles of oxygen on the top. Okay? At that point, what we need to do is go back to our equation up here and look for these ratios. And in fact, I still have them up here in red. You see that I have 2 moles of hydrogen to every 1 mole of oxygen. We'll just put those coefficients right down there. So we will put the 2 moles of hydrogen to the 1 mole of oxygen. That's from the equation. From the balanced equation. And of course, if you just wanted to double check it, the moles of hydrogen cancel. We're left with moles of oxygen. And so 7 times 1 divided by 2 is
3.5.
3.5. Okay. So now let's just do that with the water. We know that we're going to go and look for moles of water. And we're going to go ahead and keep with this 7 moles of hydrogen. Okay, this is Chem 110. So Nathan, are you here?
Yeah, I'm here.
Cool. What unit should go on the bottom?
Let's see. Mole H2. Let's see. the
And on top, what units?
mole O2.
We're gonna go
H2O.
H2O. We already did O2, that's fine. Going back in the notes, how many H2s are in that equation?
2 to 1.
2 on both top and bottom.
That is correct. Now, since I happen to do those in blue, when I underlined them, I'm gonna do them in blue again here. So it was a 2 to 2 ratio. And again, if we're clever with our units, those canceled and we have our water like we want. And so what is 7 times 2 divided by 2?
7.
7, which is what we expected to see, right? We expected if it's a 2 to 2 ratio, then we should see a 7 to 7 ratio out of that. Is everyone comfortable with what just happened there? Any questions at all?
Can you go back up real quick? I just want to see something. So you're saying 2 moles of water to 2 moles of hydrogen.
Yep.
And then the original equation was 2. Oh, okay, never mind. So at first I was confused because I was thinking it was 4 hydrogen, but it's not.
It's 4 hydrogen atoms, but we don't do that. We're using those coefficients for the species. We're not
Okay.
balancing equations anymore. We are assuming we have balanced equations at this point, and we're just going to use those coefficients as the ratio of species to species.
Okay, so our product, so basically we're looking at final product on the right? So I'm
Well,
looking
yes,
at H2O as 1. Okay,
yes, yes,
so 2 hydrogen, 2 water.
yes.
Got it, thank
And
you.
it is important that you write it as a 2 to 2. Do not simplify this. I know that, yes, it is 1, but it's important that you keep that ratio because it's one way to double check that you've put the correct coefficient in the correct spot. If you suddenly start oversimplifying things, you will run into problems. So just be cognizant of just write the numbers, don't be fancy, and just let your calculator do the work for you. Is there another question?
Yeah, how many hydrogen?
Huh?
Yeah, don't we have to now do this for the hydrogen?
No, because I told you how many.
Oh, 7. But if we wanted to, oh yeah, you already said 7. We started with that.
Yeah, we already know that one. However, I heard your other question. So Reagan asks, could I have used the 3.5 moles of oxygen to get the H2O? The answer is yes.
Yep.
So if we look at that, we could have our 3.5 moles of oxygen go into our moles of water. And of course, we'll put moles of oxygen on the bottom. We'll put moles of water on the top. And from the equation, I believe that one was in green. There was 1 mole of oxygen for every 2 moles of water. Surprise ending. Guess how many moles of water you make?
7. Let's see.
And it has to be the same, guys. It has to be the same. No matter where you start and stop, you can't make anything different. So the fact of the matter is, if I made 7 waters with the hydrogen, I better have made that when I compared it with oxygen. As long as you know the amount of one thing, you know the amount of all things. Now, I should point out, though, I would not do that. You could do it. Note, this was just a proof. I would not do this. And why wouldn't I do that, Suman?
Because because sometimes the result can be different.
Well, maybe your
Well,
math is wrong.
Yeah, maybe your math is wrong, right? If you happen to screw up this 3.5 right there, if you screw that up and you use that later on, then you're boned, right? So always go back to your original data, the data I gave you, because that is infallible, just like your instructor. And so you can always get any answer you need from the original data. So while it does work, there's no reason to not start with original data to get everywhere you want. All right, there we go. Now, I know you guys all want another one, right?
Yeah, but can I just quick ask a question?
No.
Yes, please.
What is a mole? And if I should have read this, I apologize, but is it just a way to equivalize? Like, could it also be called a midget? Or not a midget, a widget?
You can call whatever the damn mole please.
Okay,
He happened to call it a mole. I have no idea. Actually, I should look that up. Why did Avogadro use the word mole? And
Okay.
especially because it is technically M-O-L-E, and I'm thinking, why did he pick on this poor rodent? It's awful. Then again, he was a nobleman, so I guess he's used to picking on people. I don't know.
So it's just a way to equivalize it. So it's just some made up unit of measurement. but
Well, see,
equivalent.
you have no problem if I say a dozen.
Right, okay.
So just because you're comfortable with the word dozen, call whatever you want, but just become comfortable with the word mole. And
It
again,
It comes from molecule.
did he actually derive it from molecule?
Yes.
Oh, well, there you go.
Oh, that's easy. That sounds much more simple. Okay,
I actually,
thank you.
here's the funny thing. I've been doing science now for well over 30 years. I've been teaching for 15, 16 of them. And I never actually took the time. I just accepted it. Isn't that weird? I actually learned stuff just because those things that I just accept and move on. So I'm like, yeah, whatever. I don't care. That's kind of cool. He actually did derive it from molecule. All right. I assume you wikied that or something, April.
Yeah, I Googled it and it says at the end it is not related in any way to the animal called the mole.
Of course. But go ahead and look up any Chem meme, and they're going to have moles everywhere in it because we think we're funny that way. But yeah, but to answer your question, Reagan, it's just a way to scale everything up so that we can actually physically see it. It takes a molecule into the realm of being able to see it.
Okay.
So what I'm going to do now is I'm going to write the equation of 3 hydrogens plus a nitrogen going to make 2 ammonias. And this in my notes, which is why I love it when people say like, hey, can I take a picture of your notes? I'm like, it won't do you any good because my next thing says, pick a number and go. And so I'm going to say, Destiny, I need you to give me a number.
Any number?
Any number.
14.
14.5 moles of hydrogen needs how many moles of nitrogen makes how many moles of NH3. And I like this because, of course, my original problem is always going to be the trivial one, and it's always going to be the one that works out really nice in our brains. But good luck with this one. Actually, I can still do it because I'm awesome, but still, you didn't make it hard enough for me there, Destiny. All right. So since Destiny did that, is Shaw here?
Yeah, I'm here.
Okay, well, you're on deck for this one. So I want to get to moles of nitrogen
And I'm gonna ask what are gonna be very rudimentary, silly questions, but they need to be asked. Is there anything in the prompt that looks like moles?
Meaning the N2?
Meaning that 14.5 hydrogen.
Oh,
Yeah. And like I said, I'm going to be asking something that looks like you're like, wait, what are you asking? I'm going to keep asking this question over and over. And that is there anything up there that looks like fill in the blank? Because if you see something up there that looks like the quantity you're trying to determine, that's where you want to start. And so as we get these to be more and more complex, I'm going to keep asking you over and over, what looks like the thing that we're trying to find? Meaning what kind of thing has the same units as what we're trying to find? And in this case, we want moles of nitrogen. We see the moles of hydrogen. That's probably where we need to start.
so if it says moles in the question, then we need to start right there.
Yes, yes.
Okay.
But trust me, it'll get only slightly more complex here in a second. We got to keep our wits about us. So we'll do the 14.5 moles of hydrogen. Now, what units should I put on the bottom, Shaw?
You want to get nitrogen, right? N2?
Yeah, so
H2.
if I want that, I would put that on top. So on the bottom, to get rid of it, I need the
H2.
H2. And of course, on the top now, moles of nitrogen. All right, now going back up to the equation. How many moles of hydrogen do you see up there?
3.
And nitrogen?
1.
1. All right, so 14.5 divided by 3 is what, 4.825? 4.83. All right. And so let's go to, let's see, Destiny's one of my other go-tos. Destiny, we want to go to moles of ammonia. Is there anything in the prompt that looks like moles? Destiny? Radio silence. All right, Dominique, you in? All right, April, you're on deck.
Okay.
Go for it.
The 14.5 of the hydrogen.
Yes. Now keep in mind, as we do a lot of these problems, you'll find out that we keep going back and starting at exactly the same place. That is okay. If we know the amount of one thing, we know the amount of all things. And so we know the amount of hydrogen, we can get everyone else from it. Okay, so what units should go on the bottom?
The 3 moles of hydrogen.
I'm just going to start with this moles of hydrogen. We'll talk about how many in a second.
Okay.
And on top,
NH3.
moles of NH3. I always want to encourage us to not worry about the numbers. We need to make sure we're doing the problem right first. So I'll always put all the unit stuff first and then go from there.
Okay.
So if we take a look at this, now that we have the molar ratios right, because those will not cancel out.
Right.
And we're left with the things that we like.
Mm-hmm.
Now you'll go ahead and you're going to go right back up to the equation and tell me how many hydrogens
3.
and how many ammoniums or ammonia, sorry.
Was
2.
it 2, I think? 2,
2.
yeah. 2.
2. So at the end, you should probably have 6, 16,
9.66.
9.66.
Yeah.
Yep. Now, does anybody know how I knew 9.66 before anyone told me?
No.
Yeah, because you doubled the nitrogen.
Because
Oh, if you take the 4.83 and minus it from the
I doubled the
14.5.
nitrogen.
Double the nitrogen.
Huh?
No, don't do that. Don't do that. That's conservation of mass, and mass is conserved. Mold about that now, and I'll be very clear about it in our next examples. What April just did is one of the great traps. Moles. 3 + 1 is 4, but on the right I only have 2. Moles aren't conserved, but the mass is. Okay. What I did do was I looked at this ratio, as Reagan sort of intoned there. I had 1 nitrogen and 2 ammonias, so I just doubled it to get to the NH3. Now, I still got that by saying 14.5 times 2 divided by 3. That will give me the 9.66. But since I was fast on my mental math, I beat some fingers on that one. How are we feeling, guys? Massey?
All right.
Okay.
Okay.
Who else is in there? Emily. I'm gonna write your name up there because even though you didn't say your name earlier, I know I've called on you before. How you feeling, Emily?
All right.
Why do you sound questioned?
Well, I'm not questioning. This is kind of like review for me because I went over this in high school a lot. So
Oh,
I
well,
get it
that's
now.
fine.
So
But you get it now?
yeah, like I didn't remember, like it was a while since I've done this, so it's like review basically for me.
Oh, well. Well, at least you're getting it, right? So that's good.
Yeah.
Reagan's like, I love it way better than naming. Yes, some people like this way better than naming because naming is a bitch challenging. But we do have to know how to name things.
But
Okay.
like, what if you had like, so what if it wasn't just one?
What if it weren't?
Yeah. So like, what if it wasn't like?
Weren't?
Oh, shut up.
Hey, scientists need to know how to speak well too.
What
I'm
if
done
it
talk
were
good.
like H2O plus N2 or something?
So the coefficients won't matter. Everything comes out in the wash. It doesn't matter what those things are. It doesn't matter your starting values. Basically, if you set it up, which is why I keep saying what goes on bottom, what goes on top, what goes on bottom, what goes on top. As long as you set that up right and you put your numbers with the correct species, it's just calculator work at that point. There's no way to mess this up.
So like if I had like a CO2 plus N2, like the CO would just be one whole thing?
Yeah, the CO would be just one whole thing. Yeah.
Okay.
All right. Oh my goodness, let's get to the coolness. I love this. I love it. I don't care. I love it. All right. It's all fine and well to talk about these moles, but I think in all the few labs that we were able to do before the debacle that we called the shelter in place happened, did I ever once tell you to go measure a mole? Hearing nothing, I'm assuming that was a resounding
No.
shouting no, like in the movie Braveheart or something. Everyone's all lined up going, no. Yeah, we don't talk about moles. They are very useful, but they are a very hidden thing. They're the black box that ties everything together. What we do, however, is we will go and measure the mass of something. We'll measure it before and we'll measure it after, and we'll see what happens. What's going to happen on the back end or in the midst of it is the moles are going to be the thing that are going to be taking care of everything to make sure the masses all work out at the end game scenario. And that is what goes in must come out as determined by mass. Moles are going to be the gatekeepers to make sure that that holds true. And so we get to yours and mine favorite calculation that we're going to do from here to la fin de semana or semester. How do you say semester in Spanish?
Semestre.
Semestre. There we go. All right, here we go. This is the so-called mass to mole to mole to mass calculations. Your book will probably call these mass. A lot of books call them mass calculations. I don't like doing that because it is disingenuous to the process in my mind. And that process is you have to go through the moles. And so I always call these a mass to mole to mass calculation to remind me of the steps that I'm going to do. So how does this look? This looks something like this. You are going to start with a mass that is given to you. And then you are going to say these words as you draw these lines. I just realized only 2 years ago that this mantra works. It's glorious. And ever since, I've been saying it. So don't write this down, just watch me. Wow, did I just think that I was at a board and you guys were trying to copy? Oh my gosh. All right, so you're gonna say the words mass to mole to mole to mass. And that right there is going to set up your ratios that you're going to come up with. And you know that you're going to do 3 little ratios there. So what we're going to do is what the name implies. We're going to go from the mass to the moles. So you're going to put the mass of what you're given on the bottom to the moles of what you were given. Notice that on the top, your mass is now turned into a mole. Then you're going to go from the moles of what you were given to the moles of what you want. And then convert those moles of what you want to the mass that you want to determine. Now, as you have this, with this mass to mole to mass situation, you notice that across the top, you see the words mass, mole, mass. Every single one of the problems we're going to do from here to the end of the semester is always going to be something to moles to something else. And in this case, it's masses to masses. So mass to mole to mass. Now, if you are paying attention, what you'll see here with this mass to mole situation, how do we go from a mass to a mole? Let me refresh you.
The like total of whatever it is to the mole of the equation, to the how many is in the equation.
That's right.
And you also say the mass is the gram is the mole at the same time. So mass equal mole.
Masses are moles. And how did we get those masses? We went to the
Periodic table.
periodic table. So these right here, these are the molar masses. And that's from the periodic table. And guess what? Going from moles back to masses is still the molar mass from the periodic table. And then what about this ratio right here? Where did we get this ratio in the middle?
The equation.
Yep, from the chemical equation. Now, in any normal semester, I would be at the front of the class. I would say something like, despite being the tyrant, evil overlord of this class, I am also your biggest cheerleader in this class. And I would ask you, what type of rallies did cheerleaders lead in high school? And you might tell me that they led pep rallies. To remind us that when we have to go from a mass to a mass, we have to go from the periodic table to the chemical equation, back to the periodic table to get us where we need to go. All right. ¿Están listos por un ejemplo?
Sí.
Hey, I actually said that Spanglishy enough to be intelligible. I like it. All right, here we go. We're just going to do this by example because that's the easiest way. I'm going to give you an equation that we have 3 uglies. Oh man, even in online, I can hear the groans as I make a dad joke. Actually, a Spanish dad joke, I guess. My half brother is half Spanish, or half Mexican, so I guess that makes it okay. There we go. 3 iron 2 oxides plus 2 aluminums would go to make. Ooh, what type of reaction might this look like? Since we're going to do this on Monday.
Single replacement.
Say it again.
Single replacement.
Yep, it is a single replacement. We have that aluminum all by itself. So it's going to go to that oxygen. And so on the other sides, we will just make 3 irons and 1 aluminum oxide. So it's a 3, 2, 3, 1. Okay, here's my question. 14.4 grams of FeO needs how much aluminum? Makes how much iron and aluminum oxide? Now, as we do this, I want to focus on sometimes the wording here. In your homeworks, Chuck likes to be very explicit about everything, and I'm just like, that is just too many words. If I'm giving you 14.4 grams of an ingredient and I ask you how much you're going to make, what does that imply? What units am I asking you to find? Does it make much sense to go to moles?
No, it's grams.
No, of course. When I say the how much, I mean grams. Right? There's no point in asking for something besides that which I have given you. So when I ask you for how much, I want you to be cognizant. Al20. I did write Al203. Oh shoot! What the heck? Who said that? Massey? Quit pointing out my errors. I mean, keep pointing them out. Thank you. I don't even know how I said the word 3 and I wrote a 2. That's weird. Dementia.
I'm
Setting
so
in early.
sad that you started to write iron as an I versus Fe.
Oh no, that's an F, right?
No, but I thought it looked like you started with an I.
Oh, sorry, no. Oh, Jiminy. At that point, I would basically smash this computer, walk away, and turn in my keys, man. So again, when I'm asking for the how much, I want you guys to be cognizant of physically what I'm asking you for. If I gave you a mass and everything else on the other side looks like it should be a solid, yeah, I'm asking you for a mass. It'll come into play a little later that I may ask you for how much, and that might be a volume when we get into some slightly more advanced calculations in a week or 2. So I will always be asking you how much, what am I looking for, and I want you guys to constantly be assessing that. Okay, so this is 3 different calculations. We are going to go to grams of aluminum. We're going to go to grams of iron. And we're going to go to grams of Al2O3. I know this is 3 calculations. I'm already just going to set it up. And now I'm going to ask Vincent. I haven't talked to you yet. Are you here, Vincent?
Good morning, Forrest.
Sorry?
I said good morning.
Oh, good morning. Okay, good. As I'm looking for grams of aluminum, iron, and aluminum oxide, is there anything in this prompt that looks like grams to begin with?
Yes, 14.4.
14.4 grams of FeO. Now, is it too much of a stretch to say that's where I'm going to start every single time?
No, sounds good to me.
Yeah, it sounds good to me too. So why don't we go ahead and just put that there for each of them. Now, as we do this problem, I see a mass, I want a mass. Oh man, I'm getting into my cheerleader voice. If I give you a mass, I want a mass. Mass to mole to mole to mass. You can envision me in a cheerleading outfit and pom-poms cheering for you. Get that out of your brain now. So, as we do this though, we should go mass to mole to mole to mass. And know that that's what we are going to do. And so, no numbers. Vincent, what should go on the bottom?
Mass of the iron oxide.
Grams of FeO. And on the top?
Moles. 3 moles.
No. I just want units right now.
Okay.
Don't give me numbers. So then let's go to the next box. What goes on bottom?
Moles of the given unit.
Which was?
FeO. The iron. Yeah.
Yep.
Yes.
And on top, we're going to go?
The moles that we want, so aluminum.
Okay. Next box, what goes on bottom?
The moles that we want, so aluminum.
And on top?
The mass that we want.
Perfect. Now, I want to point out here, you should see this pattern, right? Everything is going top to bottom, top to bottom, top to bottom, done. There's a reason why I always say bottom to top, bottom to top, bottom to top, because your old top becomes your new bottom. So these are little patterns to sort of keep in mind as you do it. Now, let's go back to your original assessment, Vincent, and let's break you of a bad habit here early on, because you're not the only person making it. The mass of iron to oxide is 71.85. Where should I put that 71.85? With the grams or the moles?
With the grams.
Right, so 71.85. Where did we get that mass?
From the periodic table.
And how many periodic tables did you use?
1.
So for every 1 periodic table, that iron oxide weighs 71.85. Because, as all of you should in your brains right now, repeat after me, there is 1 mole on the periodic table. 1 periodic table, 1 mole. 1 periodic table, 1 mole. 1 periodic table, 1
mole.
There we go. Whoa. Was anyone else startled by the fact that my voice just dropped about 6 octaves and sounded like death himself coming to salvage my soul? 1 mole. All right.
Hey, Forrest, real quick. I think I missed this on Monday, and I just want to make sure. You are taking the Fe oxide, the iron, basically, and you're adding the mass of 55.85 for the iron and 16 for the oxygen, and that's where you're getting the 71.85, right?
Yes, ma'am.
Okay. Thanks.
Yes, ma'am. Okay, Vincent, I'm going to skip over here. Let's go to that aluminum. How much does aluminum weigh? 26.98. Where should I put that?
Next to grams of aluminum.
26.98. Hey, how many moles gave you that?
Just one.
Because there's 1 mole on the periodic table.
Correct.
Right, so now you see why I stopped you a little bit earlier, right? You tried to put that 3, but where should the 3 go? That 3 should go right here in the middle where we go to the equation. Now you can tell me how many iron 2 oxides
There was 3.
and how many aluminums?
2.
All right. This is where you worry about your equation, okay? A lot of people that he made the common freshman mistake, and he did it because I asked him to make sure that anyone else who was going to fall into that trap could see it and avoid it. When you go to the periodic table, there's 1 mole on the periodic table. There's only 1 periodic table. It's always 1. The way you go from one species to another is by those molar ratios. That's why I started this lecture by talking about the molar ratios, because this is where we're going to use them. Okay, if somebody does that calculation, you'll probably come out with something like 3.60.
Yes.
Okay. All right, so I think I picked on Vincent enough here. Did Nathan show up yet?
Yeah, you got me for an earlier one.
Well, you want to do this one then?
Sure.
Sure. Well, basically you have no choice because I'm going to bully you into it. I'm such a bully. All right. Ready? Here we go. I give you a mass. I want a mass. Mass 2. Oh man, my timing is going to slow down there. 2 mole, 2 mass. Yay, team. What units go on the bottom there, Nathan?
Grams of FeO.
And on the top?
Mole of FeO.
On the bottom?
Mole Fe. Wait.
Sorry, mole of FeO, yeah.
Yeah, you missed the O on the other one.
Thank you, sorry.
Welcome. Grams of Fe?
Not just yet. This is where we go to the mole ratio.
Mole
So
Fe, there we go.
The moles of FeO to?
Mole Fe.
And again on the bottom on the last one?
Mole Fe.
And on the top?
Grams of Fe.
Okay. So now once again, hopefully you guys see that we cancel top to bottom, top to bottom, top to bottom, top, and the top is what we wanted. Now at this point, Nathan's going to tell me how much does FeO weigh?
71.85.
How'd you get that so fast?
The top equation.
Right. Why should it change? How many moles?
1.
Okay. Skip to the end over here. 1 mole of Fe is 55.85 grams. And now, how many moles of FeO do you see in that equation?
3.
Yep. And irons?
3.
There we go. Now, if you do that, you get, what, 11.2?
Yes.
Okay.
Hey, Forrest,
Hey again.
I think I'm missing up on the math, and I feel moronic for not being able, like the top one. I'm not sure how you got 3.6.
That is an excellent question. And I know exactly what you did wrong.
Okay.
All right. So what I need you to do is the following, Reagan. Take your calculator.
Okay.
Type in 14.4 times 2 times 26.98.
Okay. 14.4 times 2 times 26.98.
Hit the enter button.
Okay.
I would like you to now say divided by 71.85. Enter.
Okay.
And now divided by 3. Enter.
Divided by 21.85 divided by 3. Okay,
You got 3.6.
I did.
Now, what you did is a common freshman mistake, and we did it in conversions. And that is, you said divided by 7185 times 3.
Yes.
And so when you do that, you told it, don't keep dividing, but now multiply that number, not divide it. So either learn to use your parentheses or do exactly what I just told you to do.
I just multiplied the bottom and then I multiply the top and then I multiply the bottom and then I just subtract it.
Then you divide it.
I mean,
Right.
yeah, sorry.
Yeah.
You know what? I completely forgot. I forgot that the 14.4 was part of the equation. That so I did what April said, except I forgot my 14.4. So had I done
Okay.
that,
Well, then I
okay.
probably answered about 8 different questions there all at once, because that's how I roll.
No, but that's no. Thank you very much. I can do that math.
Okay, good. So, but you're not the only well, you did that mistake, but other people have done the mistake that I thought you did. So,
Okay.
so I got to help 2 people at once. That's good. Okay, let's do this last one. Let's see, equals 6.81. Who wants to get me that number? Oh, Emily, there we go. So again, we have a mass, I want a mass. It's mass 2 moles, 2 moles, 2 mass.
Yeah.
All right, what units go on bottom?
Grams of FeO.
Units on top.
Mole of FeO.
Yep, on bottom.
Mole of FeO.
On top.
Is it the mole of aluminum 203?
Yep, on the bottom.
Moles of aluminum 203.
And on top.
Grams of aluminum 203.
There we go. And of course, you know, I want to point out here, does everyone notice that this step right here is exactly the same for every single problem?
Yeah.
It's exactly the same. That shouldn't be surprising. Because if we're starting at the same place, our first few steps will be exactly the same. Now, had this been a normal semester where you guys all came to school for this, I would say, look, wherever you're going, when you step out of your door, your first few steps are exactly the same. And that is, you open up your front door, you walk down the steps, you get into your car, you pull out of the driveway. All of those steps are exactly the same. Next, do you turn left or do you turn right? Well, that's determined by where you're going. And so in some of these problems, it looks like we're turning left, and in some it looks like we're turning right, depending upon our end destination. But our first few steps in solving all of these problems should be exactly the same. And so it's almost like that hesitation in Emily's voice is like, wait, am I really just writing the same thing? Yes, yes, you are, and you should be. And so it should also be no surprise that, again, we have the 71.85 grams. And that, of course, is 1 mole. It should be no surprise that it's now 3 on the bottom for the FeO. And back up at the equation, Emily's going to tell me she sees how many Al2O3s?
1.
There you go. And again, going to the periodic table, there's 1 Al2O.
3.
Massey,
Shouldn't that be 3?
can I write it out, please? Hold on. Let me get that 3 on there.
Yeah, thank you.
I don't know why that didn't take, because I know I wrote a 3. And that is now 101.96. I'm going to come back to you, Sean, in a second. Okay. Now, that number is 6.81. How did I know that?
Periodic
Reagan, how
table.
did I know that?
Because we just did the same math. We started, well, we might have gotten at it differently, but we took 14.4 times
No,
1.
no, no, no. I didn't touch a calculator.
Oh, because we doubled it. I'm sorry. We did the same thing as we did in the first one. We doubled the 3.6. Oh, no, that would be 7.2.
Yeah, see, that doesn't work. How did I do it, Reagan?
Oh, now I got it.
I think is
Periodic table.
I'm going to go old school on you. So, how did Forrest know it was 6.81 grams? Right? How did I know that? Hee 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 hee. Right? Because if I have 14.4 grams up here and I needed 3.6, and you guys told me that I made 11.2, then it follows that I have to be 6.8. 18 better equal 18. Right? 18 equals 18 grams. Mass is conserved. So that was just a way for me to basically confirm that I did all of my calculations right, because I could just add it up. So that was at 14.4 grams plus 3.60 grams equals 11.2 grams plus 6.81. So that was just me being clever in remembering that I had conservation of mass. Hey, Stuart, what do you mean by can you write it out, please? What is it?
You just did it, the math. That's what I was talking about. Just the way that you explained it to Reagan. Can you just write that out? But I got it now because you did it a couple times.
Cool. All right. Oh, let's see. Mang, since I don't actually remember, you're here, right?
Yeah.
Did I stop here or did I go to limiting reactor real quick?
Let me look at my notes.
I just want to make sure I'm either staying on track with lecture days or not necessarily going too far. In a normal semester, this would feel normal, and I would have that feel, but I think I did limiting reactant.
I think so too.
Yeah.
Okay. Yeah, let's go ahead and do it. It's only one more page. All right. So we'll be doing a lot of these types of problems in the homeworks and in some of the post-lab stuff as practices. But these types of problems right here are nothing more than the conversions that we know and love from the first exam. You start with what you know, you go with what you want, make sure all your units cancel. And in this way, it's actually better and easier than the first exam because there's only two places you go. You go to the periodic table, you go to the chemical equation, and you're done. No like looking up some conversion or whatever. All the conversions are there. They're either on the periodic table or they're in that balanced equation. I do want to talk about another application of this, and that is the limiting reactant. Now, as the name might imply, this is when you run out of an ingredient. Now, this has physical allegories. I mean, at least at my house, we do the feast and famine. My wife plans 2 weeks worth of meals, all breakfast, lunches, and dinners. And we have it all delivered and we go with that. And the pantry starts out nice and stocked. And toward the end of the couple of weeks, we're bleeding food left and right. And I go in and I say, hey, I would like to make some peanut butter and jelly sandwiches. And I look into that pantry and I see that I have a big tub of peanut butter still left over because we got the family sized, and we got a big jar of jelly because we got the family sized, but I only have 2 slices of bread. How many sandwiches can I make?
1.
1. Now, it may be that the next food delivery we got, we didn't get any peanut butter, we didn't get any jelly because we had tons of it, right? But by the end of those 2 weeks, I look in there and I'm like, oh man, I have a half loaf of bread and I've got the jelly jar looks pretty good, but man, I'm scraping the bottom for peanut butter. How many sandwiches am I gonna make?
1.
1. Yeah.
Maybe you get the bread in minute.
Yeah, we're all gonna go into but we could do this and we could do that and sliders. Nice, Nathan. Yeah, we can always find the exceptions or whatever. You could say, we can make as many sandwiches as you want. You can make a bunch of wish sandwiches. Put 2 pieces of bread together and wish you had something in the middle. But the idea here, and you guys get it, is in the first scenario, I ran out of bread. In the second scenario, I ran out of peanut butter. You will always be limited by how much you make if you have someone that's going to run out. I'm going to do an example of this and show you what I mean by it. And I'll tell you right now, there is nothing new, nothing different about this problem here than the one we just did. There is nothing different. You just have to think about something at the end of it. So here we go. I'm going to go back to my favorite here, just because it has coefficients that aren't intuitive. 3 hydrogens plus a nitrogen goes to make 2 ammonias. I'm going to ask a simple question. If 15.7 grams of nitrogen reacts with 7.81 grams of hydrogen, how much ammonia is made? Now, show of hands, how many people think the nitrogen is going to limit? Show of hands, how many people with the hydrogen? Oh, I love non-physical classrooms. I want you to keep in your mind whether you think the nitrogen is going to run out or the hydrogen is going to run out first. I want you to keep that in your mind. Pick one. Well, I feel like one of those charlatans. Pick a card, any card, put it back in the deck. Keep remembering your card. Keep remembering your card. Pick nitrogen or pick hydrogen. That's your horse. Let's see which horse wins here. When you have a limiting reactant problem, you will know that you have one because I have given you both ingredients. You know it is a limiting reactant. You know it's a limiting reactant problem when you are given the amounts of both reactants. You know, if we go back to the peanut butter example, or peanut butter and jelly example, if I just said, hey, I only have 2 slices of bread, how many sandwiches can I make? You would go like, well, I assume you have all the peanut butter and jelly you need. So yeah, 1 sandwich, big deal. If I said I had 6 slices, you'd say 3 sandwiches. But when I start giving you slices of bread and the amount of peanut butter, now you have to do the mental math to say, oh, well, if I had 6 slices of bread, that would be 3 sandwiches, but you're scraping the bottom of the jar, so that would only make 1 sandwich. So, oh, you're only going to make 1 sandwich. We're going to do the same thing here with these problems. And the easiest way to do them is you just want to do both calculations and figure out who gives you the lesser amount. So just do both calculations. The lesser amount is how much you make. So let's go ahead and do that. So I'm going to have my nitrogen going to ammonia and my hydrogen going to ammonia. So I want grams of NH3 on both of these, but we're going to start in 2 different spots. Let's see, Destiny, I haven't called on you in a while. I'm going to go ahead and show you that we are starting with 15.7 grams of nitrogen, and we're starting with 7.81 grams of hydrogen. Since it's a mass to mass, mass to mole to mole to mass. Mass to mole to mole to mass. Both of them are going to be exactly the same type of problem. We'll just have some slightly different numbers. All right, Destiny. What units go on the bottom?
The grams for nitrogen.
On top.
The moles for nitrogen.
That is correct. On bottom.
The moles for nitrogen.
Mm-hmm. On top.
The moles for ammonium.
Yep. And on the bottom?
The moles for ammonium and the grams for ammonium is on top.
Yeah. And so I'm going to go ahead and skip to the end on this. Oh, no, I'm not. I'm going to ask you, what's the mass of nitrogen? As we see it.
This is
Somebody help her out.
7.81.
Of nitrogen?
14.1.
I hear a 1401.
2802.
Yeah,
And a 2802. Is it 14 or is it 28, guys?
28 because there's 2 of them.
That is correct. Because there's 2 of them, it's going to be 20. Oh, man. Did I make this thing too small? 28.02 grams of nitrogen. And Destiny, how many moles is that?
1.
1.
Or 2.
Where do we go?
It's always
2 of them. We got the periodic table, so that's just 1.
There you go. There you go. All right. So now going back up here to the equation, where'd you go? How many nitrogens do you see?
2. Or you see 1. But
There you go. And then how many NH3s do you see?
2.
2. Do you see that, Destiny?
Mm-hmm.
Okay. Okay, so we're going to go back. We're going to go to the periodic table. So how many moles of NH3 is that?
17.
Destiny. Go into the periodic table as always.
1.
1 mole, and I'm going to go ahead and tell you that it's 17.04 grams. If you do that, you should get 19.1 grams. Sume.
Yes.
Sume, you're next.
Okay, it's gonna be gram of hydrogen on the bottom, mole for hydrogen on the top, mole for
Okay.
hydrogen on the bottom,
Yep.
mole for NH3 on the top, mole
Okay.
for NH3 on the bottom, and
Okay.
gram for NH3 on the top.
Okay. And let's see. Looks like I shouldn't have to do this. Hydrogen is going to weigh 2.02 grams. I went to the periodic table, so it's how many moles?
1.
1. I'm going to skip over to the ammonium. That looks exactly like the one right above it. It should, because we're ending in the same spot, so that should all be the same. So that is the 17.04 grams. But now, Sume, how many hydrogens do you see in that equation up there?
3 hydrogen,
And how many ammoniums, or ammonia, sorry?
1 or 2.
2.
Sorry. Yeah.
So I just want to point out that in our original one up here, we were always starting in the same place. So our initial stuff was always the same between all 3 of our calculations. What the heck? Okay, I guess that kid is okay. It sounds like I hope I don't need help. All right, so the beginning part there is always the same because we're starting in the same place. I want to point out here that the ending part here is exactly the same for each of them because we're ending in the same place. Does everyone see that?
Yep.
Oh, sorry about the kid distraction.
Yeah.
So at the end of this, 43.9 grams of ammonia would be made. Now, by doing these two separately, what this is saying is that the nitrogen, if all of it reacted, would give me 19.1 grams. The 7.81 grams of hydrogen, if all of that reacted, I would get 43.9 grams. So we have a problem here. We're not making exactly the same amount of stuff. So we got to figure out how much. And that thing, you look up there at the blue, it says just do both calculation, and the lesser amount is how much you make. So this right here is how much you made. You make 19.1 grams of ammonia using up all 15.7 grams of nitrogen. You have leftover hydrogen. Now, how much? That's a calculation for Chem 120. I'm not going to make you guys do that calculation. You could, but I'm not going to make you do it. Now, how many of you decided to pick hydrogen as your limiting because it had less grams at the beginning? Yes, April went in and did it. She goes, look, I'm just looking for the one I'm going to run out of. There's not that much hydrogen. That must be the one. You cannot do that. That is a trap, and you know I'm going to set that trap for you because I'm evil. So don't fall for it. Always do the calculations because two things are factors here. Hydrogen doesn't weigh very much, so you might not need so much. And also you have these molar ratios up here within the equation that might mess with you as well. You may need more or less depending on the molar ratios. So there is essentially zero way of telling who's going to be your limiting one just by looking at it. So you just want to go ahead, do both of them. Whichever one is smaller, that's how much you make. And this does absolutely have applications in the real world. There are many reactions where you have an expensive ingredient, you want to make sure all of it reacts so you don't waste stuff, and you have an inexpensive ingredient. So you're like, well, I'll just throw a ton of stuff of the inexpensive to make sure all of my very expensive stuff does its job. Okay, a little tag along question idea on this. Well, before I do that, are there any questions?
I do. I have a question.
Okay.
Can we do the law of or the conservation mass? Or,
No, you cannot. Well,
okay.
No. Because the first one, I'm giving you one ingredient right here and saying how much aluminum do I need. So I'm going to make that perfect. So
Okay.
I'm going to make that perfect, which means everyone else is going to come out nice and perfectly. There is no limiting reactant here. That's like saying, hey, I've got a tablespoon of peanut butter. How many slices of bread do I need? You're going to say 2. I'm going to make a sandwich, right? So I need a tablespoon of peanut butter. I need a tablespoon of jelly. So I'm going to make one sandwich. Everything is going to work out perfectly because I gave you one ingredient and said, you fill in the blanks, okay? In the one we just did, this limiting reactant problem, I gave you both of them and I said, hey, if I give you these 2, what are you going to make? Now, Reagan, you cook, right?
Yeah.
You bake, right?
Yeah.
Yeah, of course.
Sure.
Now, if I say that you want to make one cake, you will immediately go, okay, I need 2 cups of flour, I need a couple of eggs, I need a half cup of sugar, blah, blah. And you will figure out exactly how much of this stuff you have. If, however, you look in your pantry and you're like, okay, I only have 1 cup of flour and I've only got, I got a dozen eggs and I've got like a sack of sugar. I guess I'm only going to make half a cake now. Why? Because you only had 1 cup of flour, not 2. When you have all the ingredients listed, you must now, in your head, or on paper in this case, go through every single scenario and figure out just how many of your product are you going to make individually for each of those ingredients, such that you can go like, oh man, looks like I'm only going to make that much because I'm going to run out. Does that help? Probably not.
Well, no, because I'm trying to, so you're saying that 3H2 plus N2 to get to 2 ammonia, the law of conservation of mass does not apply to this. Like, I can't add up their masses and have them be equal on both sides.
No, because you're going to have too much hydrogen left over. If you come to office hours this afternoon, I will continue this problem for you and show you that you could do conservation of mass, but you're going to do one more calculation to figure out how much hydrogen is actually going to be left over to help out that mass of ammonia to balance out the conservation of mass. That is a Chem 120 thing that I will show you just to satisfy your curious brain, but I will not make you guys do in Chem 110.
Okay, so that's, okay, so we said that, we said we'll have leftover. So if I knew that number, then I could add up everything.
That's correct.
Okay. Well, can I?
Oh, look, I just answered your question. Yay.
All right, thank you.
All right. Any other questions before I do the last little concept here? Hearing nothing. I'm going to put a partial one here, partial little line, because I'm actually going to reference the thing above. I want to talk about percent yield. Now, percent yield is when you do not make as much as you predict. Remember, we started with those percentages. Percentages we're going to see probably one more time after this. The percent yield is equal to the actual amount over the theoretical amount and of course in grams times 100%. Oh, I should probably put in parentheses, think taxes. Up until this crisis, when we all still had jobs that we could go to and interact with people and otherwise not go stir crazy, maybe we made 15 bucks an hour and you work 8 hours. Does that mean you take home 120 bucks?
Nope.
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 Because guess what? They take out taxes. So if you're 15 bucks an hour times 8 hours, you should theoretically bring home 120 bucks. But you don't. You bring home 100 bucks because somebody is taking some out. So when you figure that out, you can actually figure out your tax bracket because you can figure out actual over your theoretical. And that's all we're going to do now with these reactions, because sometimes Mother Nature takes her own tax on things. So whether it's because you didn't harvest your product correctly, or maybe a side reaction happened that you weren't planning on, and that happens a lot in organic chemistry, you don't always make everything you think you're going to make. And in fact, our baking soda lab, which we've had to sort of cut because it's impractical to do a little bit, given our situation. If you do practice by doing some of the problems in the baking soda lab, that does have a percent yield problem in it. So maybe after this exam, as we're going through and doing some of the lab modules, even if we don't have one for baking soda, you might want to look at the pre and post lab questions to get versed on this sort of concept. And I'm more than happy to help you with those. They are not due, they are not for points, but it's extra practice. If in the previous example, above, we only made 18.73 grams of ammonia, what is our percent yield? Okay, it's as simple as this, guys. It's 18.73 grams actually made over that 19.1 grams theoretically made times 100%. It should be basically 98.1%. So we didn't quite make as much as we thought we would, whether it's a side reaction or whether we just didn't capture it all. Doesn't matter. The whys, it matters the what. At the end of it, our percent yield from the above calculation would have only been 98%. We would not have had 100%.
Wait, where are you getting that 19.1?
That's what we said.
Oh, never mind.
in the previous example above. That's where we're getting that. So that 19.3 is from before. Maybe I should put that. Actually, maybe I should just do this. Oh, look at that. Man, color coding everywhere. Now, the percent yield questions will be that easy, guys. Don't stress about those. Basically, you're going to do a calculation. You're going to figure out how much you should have made. I'm going to tell you how much you did make. You're just going to divide them and tell me how close to that 100% did you make it. Pretty standard. Preguntas.
Will you go the other way, saying if you made 95, if you had a yield of 95% and you theoretically could have made 20 grams, what is it? Like, what did you actually make?
Well, that is a gloriously devilish question to ask, and thank you for the idea to make your lives a living 7th level shade of Hades. No, I'm not going to.
Yeah, well, it's not that hard. It's just a different way of doing it. Okay, thanks.
Not a problem.
Everyone's like, shut up, Reagan.
Yeah, actually, did you hear that? Did you hear that?
Yeah, I heard it. Yes, I did hear it.
Yeah. So at this point, should I give you guys one to play around with for a minute?
Can you scroll up a little bit?
Raise your hand if you want one for you guys to work on for a second, and then I'll start giving you guys the thing. April raised over and over. Is April the only one? Because if she is, I can stop the recording and then just do it with her on the side. So Vincent, Winnie, okay, at least 3 people. I'll take 5%. What?
Aren't you seeing reactions?
I don't know. Where is that, guys?
Oh, I see what you're saying. I was doing reactions.
Okay. All right, so enough people here. Look at this. I'm getting up there. All right, so for you to do, I will help in a moment. So I want you guys to do this one, and I want you guys to be very careful, and I want you to dig through all of the tools in your toolbox, okay? I want you to dig through all of your tools in the toolbox. Okay, so here it is. We have C4, H10 plus oxygen. I'll be kind enough to do this part for you. What type of a reaction is that?
Combustion.
Combustion, that's right. Because we have this hydrocarbon on the left, right? This is our hydrocarbon. This is our oxygenol. So on the other side of combustion, we make CO2 and water, right? This is a combustion. Okay, my question is, ten grams of C4H10 reacts with 10 grams of oxygen. How much CO2 is made. So I'm going to let you guys start on that. So there's going to be some weird dead air. Ooh, unless I can quickly pop over and get you guys something nice to listen to. And then I will come in and start working it. And you guys can see where you've forgotten a step or maybe did something right or wrong, depending. And we'll go from there. How's that sound?
I have. Are we supposed to ignore the
Hearing
water?
nothing, I will choose the music. For carbon dioxide, I don't care how much water you make.
Okay, you just want carbon dioxide. Okay, got you.
Yeah. All right, any requests for music?
Mr. Blue Sky by ELO.
I have no idea what that is, so no.
Harry Styles.
Who?
No.
Something from the 80s.
How about Billy Joel?
Too upbeat and or too depressing.
Cinderella.
What's Cinderella?
Nobody's Fool.
Somebody in the chat said something. I don't know what they said. I'm gonna go with Pink Floyd.
Comfortably numb, please.
Huh?
Comfortably numb.
Comfortably numb, please. Ask you shall receive.
Forrest,
What?
this is Lynette. I'm still waiting on my exam.
I know you're waiting on your exam. I'll get it to you.
Okay.
Okay.
Can I just clarify the amounts were 10 grams and 10 grams? They both had 10 grams, right?
I don't know. Can you clarify?
10 grams, 10 grams. Okay, thank you.
There we go.
I thought I wrote it wrong. Okay.
All right. All right, start on that. Become comfortably numb. Okay. Now, I'm going to start going in here. All right. How many people, I'll get my participant list back up there. Pull you guys over. How many people remembered to balance the equation?
Me.
I did.
Shit.
I'm on it.
I always wait for that nice little explicative there. Yeah, so we did need to balance that equation first. You love that jerky? All right, you can have some more jerky. All right, so we should have had, let's see, I'm going to go ahead and balance it real quick. Put a 4 there, 5 there. Realize that I have 13 oxygens. That's not going to work. So I'm going to have to rebalance it here with the following. Now, April, even if you forgot to balance it now, all that's going to do is change those molar ratios. So no reason to freak out. Is Mommy back out there? No. Okay. There you go. All right, so since I gave you both of those ingredients, hopefully you started with 10 grams of C4H10, and you realized it was a mass to mole to mass, and we're going to get to grams of CO2. We're going to do the same thing with oxygen. 10 grams of oxygen, mass to mole to mass. And yeah, you can go ahead and get more jerky. There you go. All right, C4H10, what is that? 48, 58.14, I think.
Yes.
58.14 grams of C4H10 is 1 mole of C4H10. And I know from that equation that there's 2 moles of C4H10 to, I think that is 8 for carbon dioxide.
Yeah.
Okay. 8 moles of CO2. And I know that 1 mole of CO2 is 44.01 grams. I'll do the same thing for the oxygen. 32.00 grams of oxygen on the bottom is 1 mole of oxygen. I think it was 13 moles of oxygen on the bottom. 8 moles of carbon dioxide on the top. And again, we're ending in the same place. So that last little bit of 44.01 grams of carbon dioxide are the same. I actually do not have these numbers.
The top is 30.28. I'm
Okay.
still working on the bottom. Hang on.
Oh, 13, 5, 1/5. Oh, 5 over there. Whoa, it's gonna be like nothing.
8.46.
8.46.
8.46.
Yeah.
Okay. And so, how much CO2 are we gonna make? Warnock. Do not text it. I don't have my chat thing up. Talk to me.
8.46.
8.46. And why is that?
Because it's a smaller amount, and that's what we're limited
Yeah,
with.
it's the lesser amount. You always go for that lesser amount. So this is how much is made. Meaning that oxygen limits us. All right, does anybody have questions about how that went down? And does anyone want to share the traps they fell in? April already told me that she forgot to balance that equation. Were there any other missteps that people did so we can make sure no one else does?
Yeah, I actually like first I forgot to balance it, and then I also only did 2 steps. So I like didn't do I just did the moles on the thing, not the moles to the periodic table, and then the moles on the equation.
Oh, yeah. That's the reason why I always do that mantra, April, is when I see a mass, I want a mass, to mole, to mole, to mass, and I draw those lines just singing that song. You see me do that every time. I always go mass, to mole, to mole, to mass. And I do that because I don't even know how it took me like 13 years to figure out that that mantra worked, but it does. And it automatically sets up all of the boxes that you need. Did anybody else make some sort of side step there?
No, I just didn't get it as, I could have used like 5 more minutes. Like, I feel like it's taking me, I'm so slow. That was my only.
Of course it's taking you so slow. Because
we're just
you
starting.
just learned it, Reagan. I think I've been doing this a long time. Pretty soon I'll be able to say I've been doing this longer than you've been alive. But yeah, I mean, you are slow right now because you haven't practiced. So I wouldn't be too worried about that. Anybody else have anything? No? You guys want me to call it a day?
Yeah, thank you. Yeah, I think so.
All right, so I'm gonna go ahead and stop recording here.